This video is for section 9D. Speed me up using that little gear wheel. You can probably put me on 1.25 to 1.5 and watch these videos faster. Alright, section 9D is about compound events. This is where we're going to pay attention to that all-important and or. So a couple of rules coming your way. So first, when we pay attention to two events joined with the word and, it matters whether those events are independent or dependent. So we'll say they're independent if the occurrence of one has no effect on the probability that the other occurs. For example, if you flip a penny and the nickel, the events penny on heads and nickel on tails are independent. What happens to the penny is not going to affect what happens to the nickel. So when two events are independent, we're going to use the following multiplication rule for independent events. It's quite simple. I think we're up to rule 3 or 4. I'm going to put a 3 on this. Probability of A and B both occurring, right? This is both. And is associated with the word both. So the probability of both A and B occurring is a simple multiplication rule where we do P of A multiplied by P of B. So in the nickel penny example, if I want the probability that I get heads on the penny and tails on the nickel, well, heads on the penny has a probability of 1/2. Tails on the nickel has a probability of 1/2. Multiply together and you get 1/4. So what we've saved you is the idea of sample space, knowing that there are 4 equally likely outcomes, and identifying this as the one of interest. So if I was in the previous section, I would list out the outcomes and know that there are 4, and only one of them has the penny on heads and nickel on tails. But now I can just do kind of a more simple concept of multiplying 1/2 times 1/2 to get that 1/4. All right, Rob and Carrie are going to roll a die. Determine the probability that Rob rolls a 4 and Carrie rolls a 2. So if I work on that, part A, 4 and 2. Well, that's P of 4 multiplied by P of 2. There's a 1/6 chance a die will land on a 4. There's a 1/6 chance a die will land on a 2. Multiply together and you get 1 in 36. So if I were to draw a grid, as in the previous section, the outcome 4/2 would have just been one dot out of those 36 dots on the grid. Well, now I get it more simply with a multiplication rule. Rob's odd and Carrie is greater than 4. Odd and greater than 4. So the probability of odd in a die roll is 3 and 6. Greater than 4 in a die roll, well, that would only be the 5 or 6, so that's 2 and 6. Multiply together, 6 out of 36. Part C, both roll a number greater than 1. So greater than 1 and greater than 1. So that's a 5 and 6 chance times a 5 and 6 chance is 25 out of 36. No grid, no sample space needed. Simple multiplication rule dealing with the chance process of rolling a die. All right, school has 2 photocopiers. Machine A has a 8% chance of malfunctioning. B has 12% chance of malfunctioning. Determine the probability that on any one day both machines malfunction. So that would be the event MM. Malfunction. Well, it should make sense that you could think of these two machines as being completely independent and just follow our multiplication rule. So 0.08 multiplied by 0.12. Okay, 0.0096. Part B, work effectively. So let's just call that work. Multiplication rule, P work times P work. That's a complement. Malfunction and work are complements, so 92% chance machine A works. 88% chance that machine B works. That multiplies out to 0.8096. Also want you to notice that these two probabilities don't sum to 1. These are not complements of each other. So both working and both malfunctioning are just 2 outcomes in the sample space. Also notice that if we were to write out a sample space here, where we have an MM MW, WM, WW. These are not equally likely outcomes. So I can't rely on saying, oh, malfunction, that's just a 1 out of 4 chance in the sample space, because these are not 50-50 chances of working and malfunctioning. So this is your first example, seeing a sample space that has not equally likely outcomes. All right, next page. A couple has 4 kids, none of whom are going to be adopted. They'll be disappointed if they're not born in the order boy, girl, boy, girl. I happen to be from a boy, girl family. Determine the probability that they're going to be happy. So what's the chance that a family of 4 is in the order boy, girl, boy, girl? Well, births are equally likely to be boy or girl. Births are independent. So all I'm doing is that 50-50 chance each time. There's a 1/16th chance of a family being in the order boy, girl, boy, girl. So then the chance that you're unhappy, well, unhappy and happy would be complements. So you could follow that complement rule, 1 minus 1/16th. So there's only a 1/16th chance of being happy, and therefore a 15/16th chance of not being happy. Okay, 2 marksmen are firing at a target. Jiri hits the target 70% of the time. Benita hits it 80% of the time. Determine the probability that they both hit the target. Right, so that's the outcome. Hit, hit. So it's 0.70 times 0.80. All right, simple multiplication rule. Part B, they both miss the target. Missing is the complement of hitting, so we'll multiply 0.3 times 0.2 and get 0.06. Hit, then miss, well, that's 0.70 times 0.20, so that's 0.14. Benita hits, but Jiri misses. I've been doing Jiri first, so Jiri misses, Benita hits, so that's 0.30 times 0.80, which is 0.24. So notice HH, MM, HM, MH, these are the 4 possibilities. If we did this right, these 4 outcomes, all right, here's another law of probability. The probability associated with the sample space of all outcomes should sum to exactly 1. So if you added these numbers up, we would get a sum of 1. Okay, now we have an archer firing at a target. Okay, so an archer shooting at a target. Averages hitting the bullseye 2 out of every 5 shots. 3 arrows are fired. Determine the probability that the bullseye is hit every time. So part A. Probability of hit, hit, hit. So if you hit every 2 out of 5 times, you'd have a 2/5 times a 2/5 times a 2/5. And again, this is believing that every shot fired at the archery target is independent. Some people might argue that that seems a little bit unrealistic, but let's assume every shot's independent for the purpose of this. So be careful here. Sometimes it's a common mistake, but 2 times 2 times 2 is not 6, it's 8. So 8 out of 125. Part B. We hit the first few 2 times, but not the third. So that would be the sequence hit, hit, miss. So 2/5 times 2/5 times 3/5 would be 12 over 125. And we hit on no occasion. That's the event miss, miss, miss. So 3/5 times 3/5 times 3/5. That's 27 out of 125. All right, next page. All right, compound events. In the end situation, told you we had to be careful. Are our 2 events independent or dependent? So here's the dependent scenario. If they're dependent, then the occurrence of one event does affect the occurrence of the other event. So now we kind of have to tweak our multiplication rule. So in general, when we write a multiplication rule for the probability of A happening and then B happening, is we multiply P of A times the probability of B given that A has occurred. So how do we do this B given A part of this? Well, dependent events often involve sampling without replacement. Many of the examples below involve this scenario. And in these examples, we're just kind of intuitively finding that second part. And how do we intuitively do that? We make an adjustment to the numerator and or denominator of the fraction representing that occurrence. Okay. So a couple of exercises here. If I have a box with 7 red and 3 green balls, 2 are taken one after the other without replacing. So part A, both red. So remember the word both is an and problem. So it's the outcome red, red. So red, there is a 7 in 10 chance of red. But now without replacement means I've held on to that red one. So when I go to pick out red again, it becomes a 6 in 9 chance. That's what I mean by intuitively adjusting. Part B, green then red. Green then red. Well, green on the first pick, there's a 3 in 10 chance. Now that green one's been removed, so there's only 9 balls left in the box. So the chance of a red stays 7 because the one taken out was green. Next problem, a lottery's got 100 tickets placed in a barrel. 3 are drawn at random without replacement to decide 3 prizes. John's got 3 tickets. Determine the probability of winning first and second, all 3 and none. All right, let's just draw this jar. There's 100 tickets. 3 of them have John's name on it. Okay, so 3 of them, I'm going to put a scenario of John would have 3 chances at winning and then 97 chances at losing. So what's the chance that John gets first prize? Well, then it's only talking about John gets the first ticket drawn out of the barrel. 3 in 100 chance. What's the chance that John gets first and second prize? What's the chance that after mixing these 100 tickets, WW comes out? So 3 in 100 times, and here's that adjustment, 2 out of 99. Part C, all 3 prizes. Wow, really low chance of this. 3 in 100. Oops, I'm going to run out of room there. So that's 3 in 100 times 2 out of 99 times 1 out of 98. Really low chance. I'm not doing the math because that'll take too much time. None of the prizes. So losing tickets come out 3 in a row. All right, so there's a high chance of getting no prize. 97 out of 100 times 96 out of 99 times 95 out of 98. Hat has 7 names of players from a tennis squad, including captain and vice captain. If a team of 3 is chosen at random by drawing names from the hat, find the probability that it doesn't have the captain. Doesn't have the captain. So let's visualize a hat with 7 names in it. So there's a captain, a vice captain, and then we must have 5 other players. So I'll write 5P. We have 1 captain, we have 1 vice captain, and 5 other players. So what's the chance that we make a selection of 3 and it doesn't have the captain? So that means we got other than the captain on the first pick. So that would be 6 out of 7. Then we didn't get the captain on the second pick. That'd be 5 out of 6. And then we didn't get the captain on the next pick. That'd be 4 out of 5 multiplied together. Right? Because it says not captain. No C or V. All right, so that means we got player, player, player. So for player, 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 5 and 7 times 4 and 6 times 3 out of 5. All right, that ends section 9D.